Welcome to everybody. The first speaker today is Dmitry Karpinsky. He is from the National Research University of Electronic Technology in Moscow in Russia. He's also the head of the laboratory in the Scientific Practical Materials Research Center of the NAS in Minsk, Belarus. He's also a very familiar face to us all because of his 8 years spent as a postdoc in Aveiro University, and also due to his regular participation in this conference. So a big welcome back to Dmitry.
Thank you, Duncan.
Dmitry's interests are in magnetic and transport properties of solids, piezoelectricity and polarization phenomena, with special reference to diffraction methods, which brings us nicely into the title of his talk, which is Diffraction Methods, Phase Coexistence in Samarium-doped bismuth ferrate, Ceramics Across Structural Transitions. So, welcome.
Okay.
Thank you.
Thank you, Duncan. So, yeah, my presentation consists of two parts. Wasn't planned like this, but conference organizer, workshop organizer asked me to deliver a lecture about diffraction methods, and one lady couldn't do this because of pandemic situation. Hope everything is okay with she. So the presentation consists of two parts. First, about diffraction of X-ray, synchrotron, neutrons. And the second part is my original research, which is still under study. I will deliver some results. So briefly the plan, some words about sources of X-ray diffraction, how to produce neutrons, something about synchrotrons also, and how to produce about diffraction and scattering, and how to refine diffraction spectrums with some software. Yeah. And the second part is my original research. It's focused on bismuth ferrite based compounds doped with rare earths. We will check how behaves crystal structure, magnetic structure, the correlation between crystal and magnetic properties, the phase coexistence phenomena, which are observed at the phase boundary region, and how the system behaves under external stimuli, temperature, pressure, etc. So let's start with the first part, basics of X-ray. And I guess everyone knows what X-rays are. It's just electromagnetic radiation. And if we look on the spectrum, energy spectrum, the X-rays are somewhere here. The wavelength is less than 1 nanometer. And it's very useful in terms of studying matter. Yeah, because of the unit cell is characterized by similar size. In contrast to particles, like alpha particles or neutrons, we will speak later, X-rays just electromagnetic waves. And how to produce electromagnetic waves is the easiest way is to accelerate a charged particle, and it will emit like electron. It will emit electromagnetic radiation, depending on the circumstance. It can emit in X-ray energy range. So the easiest example how to emit in everyday life is antenna, how to emit electromagnetic waves and how to receive and emit. Yeah, it's a usual antenna you can find in your mobile phone. It's because of AC current. Using AC, you can stimulate antenna to emit and to receive and to convert signals. So just electromagnetic radiation. How to produce X-rays? In the lab, the most convenient device is so-called X-ray tube. The main parts of X-ray tube, I guess everyone knows. It's a cathode and anode. The X-rays are emitted from cathode because of thermal heating, and electric field accelerate electrons. They collide with anode material, and as a result of this collision, we have emission of X-rays. On the atomic level, it's a bit not tricky. Okay, the idea that only about 1% of incident X-rays produce incident electrons, produce X-ray radiation. So it's not really effective process because there are a lot of different processes, but we are interested only in this one, the force electron, which collide with the K-level electron in the atom of anode material, and as a result of this interaction, we have so-called characteristic radiation. Characteristic means it characterizes the material of the anode. As we know, in conventional laboratory diffractometers, we use copper anode or nickel or some other metals, and everyone knows that for copper, so-called K alpha radiation, the wavelength of this radiation is 1.54 angstroms. Yeah, so it's characteristic as compared to break-in radiation, because as we just said, then particle is accelerated, yeah, it emits or decelerated. So we have break-in radiation, but for scientific purposes, for diffraction, we need to get this characteristic radiation. So this is about X-rays. What's about synchrotron? Okay, it was discovered, I guess about 80 years ago as parasitic effect. So the people tried to accelerate particles like electrons, and it was a problem that the higher speed you try to get, the more energy loss you have. Energy loss because of emission of parasitic so-called radiation. And it was considered, this effect, synchrotron radiation, as parasitic, but then people estimated that it can be useful for some purposes. So this is the scheme of the modern so-called storage ring, synchrotron. And the main parts, it's linear accelerator, the booster ring where the electrons accelerate, and the storage ring where we have accelerated electrons. So what is the most important thing in synchrotron radiation? That then the speed of electron is close to speed of light. The shape of this shape of emission, it's changed from kind of torus to cone, and the closer speed of electron to speed of light, the more narrow angle of this cone. So it means the more intense radiation we have. In a relativistic case, and in case of synchrotron radiation, we have relativistic velocities. So this is a main idea, to accelerate particles up to close as much as possible to speed of light. So another idea is to use so-called in synchrotron, so-called insertion devices. So what means insertion devices? In the linear part of the storage ring, we can use so-called wiggler. It's one type of insertion devices, or undulator. They're more or less similar devices. In real life, it's several meters set of permanent magnets with oppositely aligned poles. So the idea of such device, and using magnets to make extra, to induce extra acceleration. Extra acceleration for electrons means extra emission of radiation. So, and depending on the geometry of these magnets, we can get different spectrum. Different, say on this scheme, you can see that for bending magnet without insertion devices, the spectrum is continuous, and you can, using some filters, some special optics, you can reject any wavelengths, not any of course, but within the spectrum you'd like to use for your experiments. In the case of Wiggler, the intensity, this is actually a photon flux, yeah, intensity. The intensity is much bigger because of superposition, yeah, superposition of different acts of emissions. So this is important to increase so-called brightness of the synchrotron radiation. And in case of undulator, the geometry of magnets is a bit different. And in this case, we have interference, and the spectrum becomes to be discrete, but the intensity increased drastically. So this is important features how to get really intense radiation. So in the world, there are a lot of large-scale facilities using synchrotron, and a lot of in Europe. Not a lot as we'd like to, but enough, I would say, for scientific purposes, and not only scientific. So the most popular in Europe, in France, this is European Synchrotron Research Facility, and actually I applied and didn't get a beam time there. Unfortunately, I don't know why French people don't like me, but I got some beam time in Germany, in Bessie and Desi. So a lot of around the world, and the procedure how to get the beam time. You submit a proposal, scientific proposal, and some special committee estimate your proposal, and you have to convince, you have to explain why it's so important, because it's very expensive stuff, so it's very competitive, I mean, to get the beam time. But it's possible in the, a lot of facilities just to check the deadlines. By the way, in some European centers, the deadline is 15th of February or 1st of March. So don't miss these deadlines. Let's talk a bit about the neutrons. The neutron is electrical neutral particle as compared to electron. The mass is like noted here, and it was discovered a long time ago, nearly 1990. And it's not stable. The half-life is about 10 minutes, and it decay on proton, electron, and neutrino. So the main feature of neutron for our purposes, it has magnetic moment. Why it has magnetic moment? If it's electrically neutral, it's quite easy, because it has some internal structure. It consists of 3 quarks, 1 up and 2 down quarks. And because of movement of these subparticles, we have a non-zero magnetic moment. It's quite small as compared to magnetic moment associated with electron, but it's still enough to use neutron diffraction. Neutron diffraction for refinement of magnetic structure of the compounds. So, how to produce neutrons? You can use some unstable isotopes or uranium, plutonium. They're quite expensive. And you can use particle accelerator, or you can use neutron reactor. This is the main case for international centers. The reactor can be so-called fission reactor. It means, say, uranium nuclei absorb 1 neutron, and it's split on lighter elements, and during this act, a few neutrons released. And if we can control this chain reaction, I hope we can control it. It's quite dangerous. And we can get a lot of neutrons and use them for some scientific purposes. So Next, it's spallation sources. There are some centers in the world which operate spallation source. It's PSI in Switzerland, Fission Institute, and some in UK and in the United States also. So spallation is just high energy protons hit a target, and as a result of this collision, few neutrons released, and we also can use them. And the third type of reactor, it's so-called fusion reactor. And during fusion reaction, we have light elements which transform to another element with emission of neutron again. So this is the main types how to produce neutrons for scientific purposes. I will talk about one particular example of a neutron reactor in Helmholtz-Zentrum, Berlin. Unfortunately for me and for some other scientists, it's out of operation. It was shut down about a year ago. It's personal tragedy for me. I've made really a lot of experiments there. So, and there is a scheme how it looks like the reactor zone here, and so-called experimental hall. It's a controlled area, so we have to be careful with radiation. And around the reactor area, there are a lot of instruments which use so-called hot neutrons, means high energy neutrons. And for diffraction, we have to use high energy. And another part of this center is so-called neutron guide hall, first and second one. And these instruments located in this hall operate so-called cold neutrons, so low energy. And for diffraction, as I told, we have to operate high energy neutrons like E9 instrument, and in real life it looks like this. This is a detector, and the sample is mounted somewhere here. You can use different environment, cryostat, furnace, magnet, whatever you want. And the neutrons comes from this side via neutron guide. This is another instrument. So this is E9. So what about scattering? During this process of interaction of X-ray or neutrons with the matter, we have several actions. It can be incoherent scattering, coherent, and coherent can be inelastic and elastic. So for diffraction, we have to take elastic part of this coherent scattering because we have to conserve energy of incident and scattered beams. So what I'd like to emphasize, it's a special term, so-called cross-section sigma or scattering length. So just to explain the difference between the X-rays and neutrons, we have to note that X-rays interact with electron cloud and neutrons interact with atomic nuclei. And this scattering length is a parameter which characterizes this interaction. You can say, or as an example, you can think about area of interaction. And sigma, the dimension of sigma is in area units, in square units. So in case of X-rays, this parameter has linear dependence versus atomic number of chemical elements. And it's quite understandable because the heavy element, the bigger ionic radius, and the more intense, the more intense interaction you have. So it has linear dependence, And in case of neutrons, you can see on the image the scattering length. It looks like random, and this is really strange. I mean, for some element, this parameter can be negative, and it's not easy to understand how this area of interaction can be negative, but it's reality. And for some experiment, with neutrons, you can neutralize scattering using different elements. For small angle neutron scattering, it's possible. So this is the main difference. Interaction, how the X-rays and the neutrons interact with matter. Okay, so about the scattering factors for X-ray, the formula to estimate intensity of scattering is like this. This is so-called F, yeah, here. This is so-called form factor, which we said about. It depends on atomic number. And the scattering and the intensity of scattering also depend on the geometry, on the coordinates of ions, on the wavelengths, on angle, and thermal parameter. More or less the same situation we have for neutrons. The only difference that we have B is the same parameters for X-rays. This is scattering length, and it's not linear. Yeah, but in case of neutrons, we also have component in scattering which is associated with magnetic scattering, because neutrons have magnetic moment, and if we study magnetically active material, yeah, we have interaction not only with the crystal structure, but also with magnetic structure of the material. And in the diffraction pattern, we can clarify the component from scattering on magnetic structure and on the crystal structure. So how to get diffraction pattern? It's understandable. We have to record diffraction spectrum. And how to refine it? There is one important method. It's called Rietveld. And the idea of Rietveld method is to minimize the difference between the experimental pattern and simulated pattern. To make this simulation, you have to know some model of crystal structure. And I mean, you have to know, say, space group, unicell parameters, some other parameters, and the software will simulate the pattern, and then changing different parameters, the system will try to minimize the difference between these experimental and simulated patterns. So, knowing diffraction pattern, you can get really important information about the particle size, about stresses, about some preferred orientation, and so on. So I guess everyone knows Scherrer formula, which is useful for estimation of the particle size. So there are a lot of software which use Rietveld method and assist us to refine crystal and magnetic structure of the compounds. I used this full Prof, firstly because it's free, and the second feature, it can refine magnetic structure simultaneously with crystal structure. So you can download full Prof and some other software using this link. And let's check how it works, how it looks in reality, this refinement. I've put here diffraction pattern of some complex oxide, it's cobaltite. And in case of X-ray, it looks nothing special. It has cubic structure, so few reflections, and the spectrum is refined using appropriate model. But in the case of neutrons, so we've made several experiments using the same compound. We've made X-ray in the lab, neutron diffraction in some international center, and the spectrum for neutrons looks different. Yeah, firstly because it's different radiation and different wavelengths of this radiation. And the third pattern is synchrotron radiation. And again, the pattern looks completely different. So what we have here, these three patterns, different radiation, different wavelengths, and we have, they look completely different, the patterns, yeah? Different position in two-tet geometry, angle. If I would put indices, say this reflection is located in this two-tet angle, but it's for neutron it's somewhere here, and for synchrotron it's somewhere here because of different wavelengths. Yeah? So the compound is some cobaltite with really simple structure, cubic, and we know everything about this. So in case of neutrons, I told that we also can read magnetic scattering. We can get some information from magnetic structure. So if we can make several patterns at different temperatures, so below and above magnetic transition temperature. This is room temperature, this is 2K, where we have magnetic active magnetic subsystem. And on the low temperature pattern, we have some extra reflections. Yeah, we don't have here at room temperature. Fortunately, the crystal structure remains the same. It's very important. So the only difference, magnetic scattering, yeah, contribution from magnetic scattering on the diffraction pattern. And on the enlarged part, you can see this, I guess, yeah, this magnetic pattern, this one, magnetic reflection. And here you can see red dots, experimental data, solid black line, it's a simulated pattern, the green ticks, so break positions, and we have several rows. It's because we use two-phase model. Two-phase means crystal structure consists of two different phases, and two phases for magnetic structure. So each crystal structure is associated with magnetic structure. This is for refinement. Okay, and what else I'd like to show you? What is the difference, yeah, in real situation? This is neutron diffraction, and I've put it in D space, so-called distance, yeah, not into theta, but in D, just to compare, because we use different wavelengths, yeah, for neutrons and for synchrotron, and it's not easy to compare if you look on the spectrum using 2 theta geometry. But in D geometry, it's quite easy to compare, and you can see that, say, the most intensive peak here for synchrotron radiation at 2.7 angstroms. Here it's not so intense because different scattering. Yeah, and for neutrons you have some extra reflections. You don't have here at 4.5, nothing here for synchrotrons, but for neutrons we have because of magnetic scattering. And what is the main feature of synchrotron radiation? It has a really high resolution, and using synchrotron radiation, we were able to refine that the compound has two phases, two crystallographic phases. And knowing this information, then we use it for refinement of neutron diffraction. It was important. So about the procedure, how to refine, as I told, you have to know something about the crystal and magnetic structure, and the software will simulate the pattern and compare with experimental. Of course, it's I would say the final step of crystal structure estimation. And in the full Prof suite, there are a lot of programs which assist you to get this information. What is the space group of your compound? Roughly what are the parameters and so on. Then you put these parameters in the file and the software read the file and simulate the pattern. So, and a few words about another software, Diamond. I just put 3 patterns, simulation, using different radiation, but the same wavelengths, just to show you again, highlights the difference between the synchrotron radiation and neutrons. So the intensity is different because, and the position is the same. Yeah, the position of reflections is the same. Intensity is different because different nature of the radiation, neutrons and X-ray. X-ray here, or for synchrotrons, the same. So, and I'd like to emphasize that it's a very useful software. If you refine crystal structure, it's quite common that you would like to simulate diffraction pattern and to check how it looks like. So, few phrases about the difference and about the advantages of synchrotron radiation as compared to X-ray, conventional X-ray in the lab. The main idea is resolution, and I've already told about the neutrons. The main feature of neutrons, it's magnetic scattering. So we'll not focus on this. Let me check what is the time, because I'd like to move to the second part of my presentation. It's about my ongoing research focused on bismuth ferrite-based materials. And I guess everyone knows that bismuth ferrite is so-called multiferroic, so it has simultaneously 2 ferroic order, electric and magnetic. Magnetic is because of iron ions, they're magnetically active and form antiferromagnetic structure. The problem that it's modulated structure. And it's a polar active material, so it has polarization because of, mainly because of, where is the pointer? Because of bismuth ions, which are shifted from the symmetric position, and they produce electric dipoles. And because the crystal structure is polar, so we have non-zero polarization. And the idea is to improve properties of this material. And how to improve? What means improve? To release remnant magnetization and to keep polar order, to keep polarization, and to get magnetic remnant magnetization. How to reach this? We used chemical doping in A position of perovskite structure, means we substitute bismuth ions with some rare earth elements, say, and also iron ions with some other transition metal ions. So we've made a lot of study in lanthanum-doped and the praseodymium and some other ions, rare earth elements, and the situation is quite similar. This is a phase diagram for lanthanum-doped system. When we increase the concentration of lanthanum, the crystal structure transforms from polar active rhombohedral to non-polar. Yeah, this is not interesting in terms of applications. And but here we have released non-zero magnetization. Here it's cancelled. So we'd like to be somewhere in between. And in between, in the concentration range, we have so-called intermediate crystal structure, intermediate in terms of stability. It's so-called antipolar orthorhombic. This is non-polar orthorhombic. This is polar rhombohedral. This is anti. Antipolar means opposite alignment of dipole moments. Yeah. So polarization is 0 here, but it's still interesting to study these compounds. More or less the same situation for praseodymium doped compounds, a bit different concentration ranges, but mainly it's the same. We go from R to polar active structure to non-polar with concentration, and similar situation when we heat it up, I mean increase the temperature. So we studied also different dopants, neodymium, samarium, and for samarium we found that the concentration range ascribed to antipolar, this antipolar phase is really narrow. It's about 1%. And it can be interesting because the system becomes to be unstable to external stimuli, temperature, radiation, pressure, I don't know, whatever. And mainly in this point, we play between three different structures: rhombohedral, antipolar orthorhombic, and non-polar orthorhombic. So what we've got here, we've made diffraction, you know. How to get this is X-ray diffraction patterns for compound which is in the phase boundary region. And that's why we use two-phase model. One is R phase, rhombohedral, another one is the second row, belongs to break positions of orthorhombic phase. And on the insets, you can see the evolution of reflections as a function of dopant content, and some reflection specific, say for R phase, the intensity decreases with samarium content, yeah? And some reflections specific for O2 phase orthorhombic increases. And for samarium 14, we have single phase compound, which is characterized by antipolar orthorhombic structure. So, more or less understandable. The question, the most important question you can ask, if this phase coexistence is intrinsic property of the compound or the system, or it's just because not optimized synthesis procedure. I would say it's intrinsic, because the easiest way to check is to heat the compound and to check diffraction at elevated temperature, and at some temperature you see that the diffraction show that the crystal structure is single phase, yeah. And moreover, it's if at room temperature we have a mixture of R and O2 phase, at elevated temperature we have single phase compound, yeah. But the structure is different, O1, yeah, non-polar orthorhombic. And okay, it's the situation resembles that we already observed for lanthanum and praseodymium doped compounds, and we found that 14% of samarium content means we have single phase antipolar orthorhombic structure, okay, but we tried and we've made similar compounds using different synthesis technique. For this one, we use solid state reaction, and we also repeat it with Zol-Gel method. And for the Zol-Gel, the situation is a bit different. So the same compounds, but what we find out that we couldn't observe concentration range which is ascribed to single phase antipolar orthorhombic structure. So we have a mixture. And on the next slide, I guess it's more evident. We have a mixture, either R plus O2 or O2 plus O1. So there is no concentration range ascribed to single phase antipolar. This is interesting, and this is caused, I think it's caused because of nanoscale particles we produce during Zol-Gel synthesis. The particles are characterized 100 nanometers, like this size. And for solid state reaction synthesis, we have microns, few microns, the size of average size of the particles. So it's a matter, I mean, the phase boundary, the range It's a matter of synthesis procedure. What about the magnetic structure? From our previous experience, we know that for lens non-Prosodinium doped system, we know that for rhombohedral phase, the magnetization is nearly zero. And if we have orthorhombic, like samarium-14, this is for solid state reaction, we have some released magnetization because we destroyed modulation of magnetic structure. The released, the remnant magnetization is really small because we still have anti-ferromagnetic structure. But this small magnetic moment, it's caused by non-collinear, not perfectly collinear orientation of magnetic moments. So we have some non-zero, but it's really small, non-zero magnetization. And it's understandable for us. So if we have R phase, we have nearly zero. If we have O phase, we have released magnetization. But this is the situation for solid state compounds. In case of sol-gel compounds, the situation is a bit different. So already for compounds having dominant rhombohedral phase, say 12, 14, we have non-zero, and the hysteresis loop like resemble those like we observed for orthorhombic compounds for solid state compounds. Yeah. So it's also a matter. I mean, the magnetic structure and magnetic properties also a function of morphology of the crystallites. If we look on the crystal structure using local scale methods like piezo response force microscopy, it's possible to visualize different grains which are associated. This is compound on the phase boundary. Yeah, it's a mixture of R and O phases. It's possible to itemize, say this grain is from R phase, polar active, yeah, piezo active, and this is non-polar, so it's from O phase. Okay, and this is important to estimate what we have on local scale. And with TM, with EDS, it was possible to estimate the chemical composition precisely and to ascribe, say, this grain has more O phase than this one using EDS, yeah. But the difference in chemical composition is really small, less than 1% or around. So chemically, it's homogeneous compounds, but still we have two phases on microscopic level using diffraction and on local scale. So what we have for sol-gel compounds, the PFM gives us a bit smeared picture. We cannot find, we cannot associate particles and PFM domains. It's because the particles are really small. On using SEM methods, we can estimate this. So, and the average size decreases with dopant content. The average size is a few hundred nanometers. Yeah. So, and this is important in terms of phase coexistence, in terms of magnetic properties. And based on these data, we constructed the phase diagram. And for solid state ceramics, we declare that there is a region, the concentration. There is a region which is ascribed to single phase O2 structure, antipole. And this region is a coexistence of R plus O2, and this is O2 plus O1. This is okay, it's understandable for us. For sol-gel compounds, we couldn't find this region. So everywhere we have a mixture, either R plus O2 or with antipolar or antipolar plus non-polar structure. So it wasn't possible to find a single phase compound with O2 phase. And looking on the PFM images performed or recorded for Zol-gel compounds, we found out that even for compounds which we think as single phase, they still have some inclusions. Single phase, say, are polar active. We still have some inclusions which are not active. And in opposite situation for non-polar compounds, which are characterized by O1 phase using diffraction technique, we still have some active PFM. Yeah, and it looks like the phase coexistence region is different when we check it using microscopic method and local methods. Say using TM, we were able to find out, say, for 8% of samarium content, which is considered to be single phase rhombohedral, we were able to find some clusters, local nanoscale clusters with orthorhombic structure. But these clusters are invisible for diffraction because if you remember, such parameters as scattering length, for diffraction is something about 100 nanometers. And if we have some inclusions with nanometers, 10 nanometers, we cannot detect these inclusions of extra different phase using diffraction methods. And the same story for other compounds. So using local scale methods like PFM and TM, we found out that the phase coexistence region is a bit different as we thought about using diffraction results. So, and in reality, this phase coexistence is a bit wider in both directions. So on local scale, we find out that here we have some inclusions in R phase. We think it's single phase compound, but it's not in reality. It still has some inclusions of O phases. This is important to understand the phenomena which we observe on the phase boundary region. So a few words, I think I have some minutes, yeah. A few words about external stimuli. Why we took this compound samarium 14, or around this composition? Because the phase coexistence means high sensitivity of the system to external stimuli. External stimuli means radiation, pressure, temperature, and this is interesting if we'd like to design some sensors, to make materials which are sensitive and to read some response when we expose it to some stimuli. So we applied pressure, quite high pressure, to our compounds, and we checked X-ray diffraction before and after application of high pressure. And what we found out that the crystal structure transforms if we had single phase R rhombohedral. Before application, after application of high pressure, the crystal structure becomes to be more orthorhombic. So we move this balance, we shift it to orthorhombic phase, and the phase boundary will be different. It's, I would say, quite understandable because the orthorhombic phase is characterized by smaller unit cell volume, and we apply high pressure. It means we compress. Compress means we stabilize phase, which is characterized by smaller unit cell parameters. So this is important. I mean to show the sensitivity. We can control or we can stimulate phase transition using external stimuli, not only temperature but also high pressure. And the same story, we have the same modification. We have analyzing magnetic structure, magnetic properties. Before application, I already discussed about this, orthorhombic and rhombohedral compounds, the modification. And when we applied high pressure, we shift this balance, shift the crystal structure from R to O, and the magnetization curves resemble those we observed for orthorhombic, for all compounds. So this is understandable because we drastically changed the morphology of the crystalline. This is some image for compounds before, these Zol-gel compounds prepared by Zol-gel method, before application of high pressure, and this is image, the same scale, I hope, more or less, after application. So the average size decreased drastically several times, and the density becomes really high. The density, porosity is very low. So this is important. And I would say I have to finish, yeah. So about the conclusions, what I'd like to emphasize that depending on the synthesis method, we can control the phase boundary region. Yeah? And the crystal structure, we can stabilize either R dominant or O orthorhombic phase. And this is important to control phenomena observed at phase boundary region. And another important thing that on local scale, the situation is a bit different. And we got this external data, which enriched the image. We got the image of the phase diagram. We've got using diffraction microscopic methods. From microscopic method, we have one situation. On the local scale, we see the situation is a bit different, and the phase boundary region is a bit wider than we thought. So I'd like to thank you for your attention. I'd like also to thank my colleagues who assisted with measurements in different, in Vilnius, in different scientific centers in Aveiro also, and in Germany, and we work together in frames of our joint RISE project transfer, which is sponsored by European Commission and assist us to move between these units. Unfortunately, now we have to sit at homes, but hope we can plan in nearest future our business trips. So thank you again.
Thank you very much, Dmitry. A very interesting talk, obviously telling us the difference between synchrotron and neutron radiation and the different information that we can get and how these different pieces of information can actually be complementary to each other. So thank you very much for an interesting talk. Obviously now we're open for questions. If anybody has a question, please say.
I have a question.
Igor, please.
I have several questions. No, thank you very much for very good presentation. But Dmitry, I'm not understand clear several slides with neutron diffraction, maybe like 15 slide and 17. When you show diffractogram with split peaks.
Let me
neutron. Maybe you explained before. I think neutron diffractogram or several X-ray or 15 maybe.
So this one, yeah?
No, for example, this is, yes.
2.8 in this space. So it means that, okay, this is very, very important, yeah? If we compare the same reflection recorded by synchrotron radiation, yeah, we distinctly see the splitting, yeah, because of high resolution of the
yes, and okay.
of instrument. And using neutrons, we cannot resolve this reflection. But in reality, it's splitted. It's splitted because the crystal structure, it's not a single phase. We have two phases. And it was able to say that we have two phases only after measurements using synchrotron radiation. When we got this information, we construct the model, two phases model, and we use it to refine neutron diffraction pattern. Two phase in terms of crystal structure and two magnetic phase. And this is, it was really important because one crystallographic phase belongs to antiferromagnetic order and another one to ferro. And it's very weak, but it's important. So this is really interesting to combine different techniques. yeah, to show the advantages of different techniques. With neutrons, we can read magnetic scattering, magnetic contribution, and with synchrotron, we got the best resolution we can reach.
Okay.
So it's, in reality, it's splitted.
Okay. In this case, what is resolution of neutron diffraction is less?
Yes.
It's less.
Usually it's less. Usually it's less. You cannot reach resolution using neutron diffraction. Any instruments around the world, you cannot reach the same resolution you can get using synchrotron radiation. Even for so-called special instrument like E9, it's called firepot, fine resolution something. And yeah, this is interesting. I mean, to combine different methods.
This is important and it's useful.
Yeah. So resolution matters.
Okay, thank you.
You're welcome.
I have another question.
Let's see if there's anybody else with a question first, and then we go back to you, Igor. Is that possible? Any other questions?
Probably Vladimir would like to ask, but I cannot hear.
Sorry. Dmitry, listen me.
Yeah.
Such question. You have very fruitful, interesting description of method, various methods, such as very strong science about structure and property of this material. Material very interesting. It is ferroelectrics, ferromagnetics, and antiferromagnetics. I don't know this structure in many such a subject, but such question: how now is application of this material? Do you know some perspective for this composites application of magnetic ferroelectric properties in such devices?
Okay, this is quite difficult for me because everyone forced me to make some practical applications, and I'd like to make fundamental science.
No, I see you.
Yeah, so I will answer. Okay, it's possible. Yeah, it's sensitive. I mean, say bismuth ferrite doped with some elements. It can be useful for some sensors of magnetic field or electric field. But the problem it's the sensitivity is not comparable with commercial materials, and not comparable with composites. This is still...
Yes, no, it is some new material, very interesting, maybe so some future.
It's more for fundamental interest, not for real application right now.
No,
but
yes, I understand.
How it works, how to play with phases and how to control.
Okay, okay, very nice. Thank you, Dimi.
Thank you, Vladimir.
Okay, Igor, would you like to make your second question?
Okay, about PFM imaging,
let me scroll.
As I understand, practically always you have a piezo response or not.
That's okay.
As I see, it's always is present, but if not, in any case, it's possible to switch.
To find.
Yeah, yes. What is?
Igor, you know better that it's everywhere. It's possible to find some non-zero. See here, roughly you can see. You see this image. Yeah?
Yes.
This is quite distinctly. You can say, okay, this grain is neutral, PFM neutral. Yeah, and this is it has some contrast. So for this compound, with big grains, you can say this is non-active. So O phase, non-polar or antipolar, and this is R phase. And inside R phase, you can stimulate, play with domain, and so on. So looking at this image, I would say we can distinguish different phases. For Zol-gel compounds, where we have really small grains, nanometers, it's a bit different. Probably it's a bit different also because of polishing procedure. Yeah, before measurements, we polish it, anneal it, and use some chemicals. And probably when we have really small grains and during polishing procedure, you average and you smear or you diffuse. Yeah, you read some average signal from different grains. So it's I would say it's a question of experiment. Yeah, it's not because of material.
But if you do polling some area, maybe it will more clear to see. Maybe some grain it will not switch.
It's a bit tricky, and you have to be careful with polishing because you induce mechanical stress in the surface layer. Yeah, and when you have a chemical composition close to the phase boundary, which is very sensitive to any external stimuli, also mechanical. Yeah, you can modify, and it's not real situation. I mean, in the bulk and the surface layer will show you different signal. It's not representative for material. It's representative for this thin upper layer surface only. So we have to be careful with interpretation. And you have enough experience, I know.
Yes, in any case, picture is good, resolution is good, but
yes,
if you have this is a simple system, but it's not so simple.
Yeah.
A small question about high pressure measurement, Dmitry. One question: how you did? X-ray. I think X-ray on the
after.
And after, yes, and after magnetic measurement.
Also after, so we applied.
How do you apply 5 gigapascal?
Using a special equipment, press.
X-ray, okay, this is maybe some the diamond cell.
This is,
okay, this is understand, but after you show magnetic measurement.
Yeah, also after application of high pressure, we took this pellet and make magnetization measurements.
This is micro volume, yes, it's small volume.
Yeah, it's a few milligrams.
Yes, this is small. Okay.
So we can.
Because you don't show any technical.
Actually, I applied to ELL. It's in Grenoble Institute. Yeah. And it's possible to make in situ measurements under high pressure. But,
this is how is diamond cell, yes?
Diamond cells, yeah. And this is important for another compounds, for another system. But it's very competitive, and I couldn't get a build time there. In France, they don't like.
Now I understand. Okay, thank you.
Oh, you're welcome.
Okay, yeah, I really will stop everybody now because coffee is also very important.
Yeah, true.
So thank you again, Dmitry, and we are back here at 10:30. Okay.
Okay.
Okay. Thank you very much.
Thank you. Bye.